Hey everyone, today we're going to learn about the electrodeposition of tin and its allotropic transformation. But first, what is electrodeposition? Electrodeposition is a method to produce in situ metallic coating by the action of an electric current on a conducting material immersed in a solution containing a salt of the metal to be deposited. In our case, the solution where the conducting material will be immersed is stannous chloride. The tin too will be reduced to metallic tin. This beta tin, or also called white tin, is electrodeposited on the cathode. Later on, this metallic deposit is collected, as we will see on this video. This is the principle that this experiment relies on. So, what materials are we going to use to start our lab experiment? In contrast to a galvanic cell where oxidation and reduction half-cell reactions occur spontaneously, in an electrolytic cell we need an external current, potentially allowing for the semi-reactions. For this, we will need a power source that supplies a DC, a direct current. You can use different types of methods to get the current you need. For instance, you can use batteries with different nominal voltages. But in this case, we're using the power supply model 135063. Then we need to connect our electrodes. The anode that we're using in this cell is a paperclip. The cathode is a platinum wire. We also need a 10 mm beaker to set up the electrochemical cell. Crocodile clips for electrically connecting the power supply with our electrodes, a washing bottle, filter paper, test tube and Bunsen burner for melting our tin crystals, an Eppendorf tube for sample storage, a pipette with its handler, and of course our chemicals. We're going to use 5 mm of a 2 molar stannous chloride solution in hydrochloric acid and distilled water. Also, an ultrafreezer to allow the allotropic transformation from beta tin to alpha tin, or also called gray tin, at low temperatures, which are below 13.2 degrees Celsius. A microscope to observe the tin crystal, and do not forget to protect your hands from chemicals by wearing rubber gloves. So, let's begin. First of all, in order to achieve our goal, we must build an electrochemical cell. These are the steps you need to follow when building an electrolytic cell. First, check that all the materials that you need are clean and in good condition. Then you have to properly connect the wires to the power source. Those wires will be connected to the two selected electrodes. Remember, the anode goes to the positive terminal and the cathode to the negative terminal of the power source. Then we add the electrolytic solution to a beaker. Once we have our electrolytic solution, we place our electrodes into the solution and we adjust them properly. You will have a cell that looks like this. But what happens at the molecular level? To achieve the electrodeposition of tin, we have a redox reaction occurring in our cell. Let's take a look at the half reaction for reduction. We have that the tin 2 plus ions will be reduced to metallic tin, coating the platinum cathode. Let's go back to our lab. We set the values for the power source at 1 ampere and 10 volts, and then we started. Then tin 2 cations travel through the electrolytic solution to the cathode, where they are reduced and deposited on the surface of the platinum electrode. As we see here, the crystallization of tin is happening. After a few seconds of applied current, we stop the reaction, and then we collect the white tin layer foam in the cathode. First, we carefully remove the tin crystal from the platinum wire with a spatula. But what will be the structure of the tin crystals under the microscope? Some of the deposited metallic tin is collected and observed under the microscope, as you can see here. By following this procedure, it is expected the obtention of beta tin deposit, which is a stable allotropic form of this metal at room temperature. This beta tin has a body center tetragonal crystal structure, as we can see here. Now, it is necessary to collect tin deposit a bunch of times. Then, we rinse the collected white tin with copious amounts of distilled water using filter paper and a funnel. Remember, we need a high purity tin sample to allow the allotropic transformation. Then, we scrape the tin solid from the filter paper and place it in the test tube. Using a Bunsen burner, we carefully melt down the tin crystals to obtain an uniform tin pellet. Remember, the test tube must be moved back and forth over the flame to make the heating uniform. Now to the ultrafreezer. First, we're going to cool our sample at room temperature and store it in an Eppendorf tube. Then the sample is placed in an ultrafreezer at -80 degrees Celsius for 1 week. A complete allotropic transformation from white tin to gray tin should be observed after this period. But what happens to the white tin? The white beta tin has a body-centered tetragonal crystal structure at room temperature. It transforms below 13.2 degrees Celsius to gray tin, which has a diamond cubic crystal structure. The rate at which this takes place is extremely slow. However, the lower the temperature below those 13.2 degrees Celsius, the faster the transformation rate. Accompanying this white to gray tin transformation is an increase in volume, around 27%, and accordingly a decrease in density, from 7.3 grams per cubic centimeter to 5.8 grams per cubic centimeter. Consequently, this volume expansion results in the disintegration of the white tin metal into a coarse powder of the gray allotrope. That is all for this experiment. See you next time.